Hello everyone, and welcome back. Today we're going to be continuing our exploration of Markov processes and discuss a particular type of Markov process known as a regular Markov process. So, in case you haven't already brushed up on your basics of Markov processes, definitely make sure you know what a Markov process is, what the Markov property of a Markov process is, and also knowing a little bit about, what it means for a state to be absorbing might also be a little bit useful too. Now, in the last video, when we talked about absorbing Markov processes, we introduced the topic of regular matrices. And we say that a matrix P is regular if we exponentiate it a finite number of times and we have a bunch of entries that are all positive, none of them equal to 0, for some finite number in the set of natural numbers. And we're like, okay, well, how can we see if a matrix, in particular a stochastic matrix P, is regular? Well, if we look at the matrix directly and we see no 0 entries in that matrix, then that's what we refer to as trivially regular. And the Perkins theorem guaranteed that if M is equal to n minus 1 squared plus 1, where n is the number of rows or columns of our stochastic matrix, then if P to the power of M is trivially regular, then the original matrix P is guaranteed to be regular, and M actually is the smallest value of the power that you have to actually consider. Right? Now, for our discussion about regular matrices or regular Markov processes, you definitely need to brush up on your eigenvalues and eigenvectors because that's going to play a huge part today. So the very first theorem is actually associated to the eigenvalues of a stochastic matrix, and keep in mind a stochastic matrix need not be regular or absorbing in terms of its process for this theorem to take place. And this theorem says that if we have any stochastic matrix, even if it's left, right, or doubly stochastic, one will always be an eigenvalue for that stochastic matrix. So let's see if we can provide a nice little proof for this. So let's assume that P is right stochastic. I know that we've been primarily working with left stochastic matrices, but the proof of this is actually a little bit more direct in the right world. So when we say that P is right stochastic, that means the sum across all columns j is equal to 1 to n of P ij. This is going to be equal to 1. So this is obviously a row sum. So that's the first property for it to be right stochastic. And the second property is true for also left, that Pij belongs to 0, 1. And that has to be true for ij ranging from 1 to m. All right? So that's what we mean by right stochastic matrix. Also, let's assume that 1 hat is a m by 1, let's assume that P is n by n, a n by 1 vector of all ones, right? So for example, 1, 1, 1, that would be your 3 by 1 ones vector. Right? So what we're going to do is we're going to take our stochastic matrix P and multiply it by this vector of ones. So when we do that, we're going to have P times 1, and you should be able to see that that's actually equal to 1 times the 1 vector. Right? And that's primarily due to the sum via dot products because, it's the first row times that column of ones, and the first row sums up to 1. So when we multiply all those entries in that row, 1 each, and then add them up, since the sum is equal to 1, because if we multiply that by 1, the jth entry of 1, you're still going to get 1, right? So we're going to have that's equal to the 1 vector, in particular, the matrix times the 1 vector times the scalar 1 times the 1 vector as well. So from this equation, if you know anything about eigenvalues, you should be able to see that 1 is an eigenvalue of P. Right? Now keep in mind, I did say that this is true for any stochastic matrix, right or left. Keep in mind that if 1 is an eigenvalue of P, then properties of eigenvalues, 1 is also an eigenvalue of its transpose. Right? So if P has a eigenvalue of 1, then its transpose also has an eigenvalue of 1 as well, right? So if P is right stochastic, that means P transpose is left stochastic, and therefore, regardless of the type of stochasticity of this matrix, 1 will always be an eigenvalue for that, right? So that's actually going to be a very important theorem when it comes to regular matrices and regular Markov processes. Another very interesting theorem is the following. So if lambda is an eigenvalue of our stochastic matrix P, regardless left or right, then the magnitude or the size of those eigenvalues will always be less than or equal to 1. Keep in mind the eigenvalues could be complex. They could be equal to I or negative I potentially. But this says that regardless of the eigenvalue I have for P, so let's assume that this is the real part of the eigenvalue of lambda, and this is the imaginary part of lambda, then if we draw a unit circle, then all of the eigenvalues will always be within the circle or on its boundary, with one of the eigenvalues from the previous theorem guaranteed to be right there. So that's our one eigenvalue. And in order to prove this, if you remember the Gershgorin circle theorem, it actually provides a very nice way to justify this. Now let's take a look at a particular regular stochastic matrix. And keep in mind, if you have a stochastic process that satisfies the Markov property, then we usually call that Markov process a regular Markov process, provided that the stochastic matrix is indeed a regular matrix. So what we have here is a regular, so we have a regular left stochastic matrix. So what is actually so special about regular Markov processes? So if we take this matrix and exponentiate it, so p squared, what we're going to have is 0.16, 0.84 for the first column, 0.12, 0.98 for the second column. Before I keep on giving you a few more iterations of this, I want you to look at 0.3 and 0.7 and 0.1 to 0.9 and notice that these columns are very different from each other. But if I look at the columns of p squared, for example, these columns at least appear to be a little bit more similar to one another. Obviously, this might give this next statement away. So if I look at p cubed, for example, what you're going to have is 0.13, 0.87, 0.12, 0.88 approximately. And if I continue onward, for example, P4, you're going to have this is approximately equal to 0.12528, 0.87472, 0.12496, and 0.87564 approximately, right? And if you notice that these columns are equal to one another, up to 2 decimal places. So what exactly is going on here, and does this really have anything to do with regular stochastic matrices? Indeed, yes. So what I want to do is I want to take the characteristic polynomial for this matrix, right, which, keep in mind, if you don't remember how to find the characteristic polynomial, is just the determinant of our matrix minus lambda times the identity matrix of the same size as P. Once you do this for our particular stochastic matrix, you're going to have once factored 1/5 times 5 lambda minus 1 times lambda minus 1. This lambda minus 1 you should not be surprised with seeing, because we've already proven that lambda is equal to 1 is always an eigenvalue for a stochastic matrix, right? So that's not surprising. So lambda 1 is equal to 1, as we clearly see here. And we see that lambda 2 is equal to positive 1/5. And notice that, of course, that the magnitude of 1/5 is strictly less than 1. So if you find the associated eigenvectors, for example, an eigenvector for lambda 1 can be found to be 1, 7, or any scalar multiple thereof. And you can also find that the eigenvector v2 is any scalar multiple of the vector 1 and I believe negative 1. Right? So once you have these two vectors, what exactly can you get out of it? So one of the very beautiful theorems about stochastic matrices, in particular if you can have this eigenvalue of 1, is that you can always make the values in the associated eigenvector either both positive or both negative, right? So you're never going to have where the entries of this eigenvector are going to be opposite signs. That will never happen for stochastic matrices. So if we can always make the entries positive, then that means we can also make the entries into a probability vector, right? So if this is a probability vector, that means we need to sum the values such that the sum is equal to 1. So if we do 1 plus 7, that's obviously going to be equal to 8. What I'm going to do is I'm going to choose a particular eigenvector for lambda is equal to 1, and I'm going to define it as q. And this is going to be equal to 1 divided by 8 and 7 divided by 8, which in decimal form is 0.125 and 0.875. So what is so special about this matrix, or this vector? So if we go back and look at the original matrix when we exponentiated it, look at the similarities between those two. So is there any way that this happens just by chance? Actually, no. Right? So this is the columns of Pn for large values of n. Right? And this leads us into the theorem that states really what is going on here. Right? So what does it say? So let's assume that P, n by n, is a regular stochastic matrix. So here we're requiring that our stochastic matrix is regular. If you have a stochastic matrix, then the following things are guaranteed for you. If we take the limit as n goes to infinity and exponentiate our stochastic matrix, this matrix exists, it's also unique, and it is also stochastic. So the limit as n goes to infinity of p to the n exists, is unique, and is also stochastic. So if we go back to our original example and exponentiate it more and more and more, it will get closer and closer to some matrix. Right? Now what matrix is that? Well, we see that Q was the columns of our matrix. Maybe that's just a special case, but what exactly is going on here? Well, aside from that, what else can we say? So let's assume that P0 is any initial state probability vector. Initial state probability vector, in particular for x0 for our associated stochastic process. Then, if we take the limit as n goes to infinity of our stochastic matrix exponentiated to the power of n multiplied by our probability vector for x0, this is going to be equal to q, I'm going to call it, is the associated probability vector for eigenvalue equals to 1. So if you exponentiate n infinitely many times and multiply it by your initial state vector, then you're going to get q. And more importantly, this is true for any p0. So we can start literally in any state, and it will always converge to this vector q. And what's very special is that we don't even need to consider the initial state if that is true. So there must be something more special about this matrix P. And in this case, we have that this matrix is regular. So the third property actually introduces where this Q comes from, and it says that all columns of the limit as n goes to infinity of p to the power of n are Q, this limiting vector. Okay, so that's actually very, very interesting. And keep in mind, this vector Q is sometimes referred to as a limiting probability distribution of your stochastic process, Xm. All right, so let's look at a actual numerical example to sort of see what's exactly going on here. So let's assume that we have this left stochastic matrix given here to be 0.8, 0.1, 0.1, 0.1, 0.2, 0.7, 0.1, 0.7, 0.2, which is obviously a left stochastic matrix, and it's trivially regular. And if we look at the transition diagram, where we have three states, S1, S2, and S3, everybody is going to have a probability in this particular picture. So we have that from 1 to 1, we have 0.8. From 2 to 2, we have 0.2. From 3 to 3, we have 0.2. From 1 to 2, we have 0.1. From 1 to 3, we also have 0.1. From 2 to 3, we have 0.7. From 2 to 1, we have 0.1. And from 3 to 2, we have 0.7. And lastly, from 3 to 1, we have 0.1. So that is our transition diagram. Notice that the dominant probabilities, 1 is likely to transition to 1, 2 is more likely to transition to 3, and 3 is more likely to transition to 2. So one could guess that, okay, maybe 2 and 3 are sort of isolating back and forth to each other, and 1 is sort of going to chill, in its own little world as n gets closer to infinity. So if we look at the eigenvalues of this particular matrix, as you already know, eigenvalue 1 is always going to exist, and we're also going to have two other eigenvalues, lambda 2 and lambda 3, and you can find that these are going to be equal to 7/10 and negative 1/2. From these eigenvectors, you can find your associated eigenvectors v1, v2, and v3 to all be equal to 1, 1, 1. The next one is going to be minus 2, 1, and 1, and the last is going to be equal to 0, minus 1, and 1. The only interesting one that we really care about here is the one that is associated to 1, and that's this vector v1 is equal to 1, 1, 1. So if we make this into a probability vector, what you're going to have is you're going to have q is equal to 1/3, 1/3, and 1/3. So this is going to be our limiting probability distribution for our stochastic process. So that means for large n, we don't actually need any conditional probabilities, because we can say with confidence that the probability that the nth state is in state 1 is practically equal to 1/3. The probability that xn takes the state of S2 is practically equal to 1/3, and the probability that xn is equal to S3 is probably equal to 1/3. So even though the initial state and the transitional states are all very different, practically what you see here is that the probability distribution for xn is a discrete uniform distribution for long times n, right? So again, this is called the limiting distribution. In this case, a probability mass function distribution of the Markov chain C is equal to Pxn. And this limiting distribution is guaranteed to exist and also is unique since our original stochastic matrix P is regular. So as you probably are wondering, yes, there are Markov chains that do not have a limiting distribution. I'm also going to throw in this word here, unique limiting distribution, provided that the Markov chain is not a regular Markov chain, right? At least up to this point, we have that if we have a regular stochastic matrix P, then we obviously have a unique limiting distribution Q, right? So that means every regular Markov process has a unique limiting distribution. So a natural question that you may be asking is, okay, well, what about irregular Markov processes? What about irregular Markov processes? Let's actually look at a couple very trivial examples of them. For example, let's assume P is equal to 1, 0, and 0, 1. So if we have 1, 0, and 0, 1, what we have here is that S1 and S2 practically stay in their own little orbits, right? So as we clearly see, all states are absorbing states. All states are absorbing states, which means that we have an absorbing Markov process, or an absorbing Markov chain. And if we look at the associated eigenvalues and see what they're doing, so the characteristic polynomial for P in this particular case, one can find, is actually lambda minus 1 squared. that's also should be very trivial too, because we have a diagonal matrix and we have 1 and 1 to be our eigenvalues, right? So we have that lambda 1 equals lambda 2 are both equal to 1, right? But what about the eigenvectors? So v1 is going to be equal to c1 times 1, 0, and v2 is going to be equal to any scalar multiple of the vector 0, 1. So notice that both of these can be made into probability distributions. Actually, they are probability distribution vectors, right? So what you have here is two limiting distributions, right? So which one is which? Well, it really depends on the state you start in, right? For example, if I have an initial state vector of 1, 0, I'm going to have 1, 0 forever, right? So for example, Pn of 1, 0 will be equal to 1, 0, and for example, Pn 0, 1 will always be equal to 0, 1 forever, right? So as n gets close to infinity, obviously these do not change since we're dealing with an identity matrix, but those would be the limiting distributions, but they are dependent on the initial condition, right? So for regular Markov chains, it doesn't really matter the initial condition. We always converge to the same exact point, or the same exact vector, or the same exact distribution. A few different ways you could actually look at that type of process. But when we have an irregular Markov process, at least in this particular case, what we have here is, depending on the initial condition, we have two different places that we could actually converge to. Let's actually look at another example of an irregular process. And this is actually very closely related to the identity matrix, but it has a little row swap in it. In particular, 0, 1, 1, and 0. So is this a regular matrix? That's the first thing we need to investigate. So if we do p squared, what we're going to actually have here is 1, 0, and 0, 1. And if you multiply p squared into p cubed, what you're going to see is 0, 1, 1, 0. And if you get to this point, you're probably like, okay, now it's going to repeat. So we can generalize this and say, okay, well, p to the 2k will be equal to 0, 1, 1, 0, and p 2k plus 1 will be equal to 1, 0, 0, 1, and k can belong to the set 0, 1, 2, and 3 to have these recursive relations. So what you have here is you have two states, S1 and S2, that are forced to dance between themselves, and you cannot stay in their original position. So it's almost like a very restricted, bounded, one-dimensional random walk, but you only have two places where you can stand, right? So we have probability 1 here and probability 1 here, right? So since it goes back and forth and back and forth, so for example, after one state, if you start at S1, then you're in S2, and then after two states, you go back to your original state. This is usually what we refer to as a periodic Markov chain, right? And here, S1 has a period of 2, and S2 also has a period of 2, right? So if you look at all of the objects in this little set or class, what you have there is every element in that set has a period of 2, since that's a nice little periodic Markov chain. Now, lots of theory can be associated to periodic and also aperiodic Markov chains, but we won't get into them there. But we clearly see that this does not have a limiting distribution regardless of the initial condition. And even if you pick an initial condition, it still will not have a limiting distribution, right? So for the identity matrix, we had two limiting distributions. Here we don't have any, right? So for periodic Markov chains, we do not have a limiting distribution, even if it's not unique, and that's quite sad. Let's actually look at another Markov process that you probably are already familiar with, and that's in particular the Ehrenfest processes, right? So if we look at an Ehrenfest matrix, in particular for Cardinal set S is equal to 4. And if you don't remember what Ehrenfest matrices are, that's the number of particles that are between two states, where the number of particles are capped below by 0 and capped above by n. In this case, we're choosing 4. So that means their state space is going to range from 0, 1, 2, and 3. So the associated Ehrenfest matrix for this particular process is going to be a 4 by 4 matrix, obviously. And we're going to have 0, 1, 0, 0, 1 third, 0, 0, 0, 2 thirds, 0, 2 thirds, 0, and 1, and finally 0, 0, 1 third, and 0. Right? So that's our Ehrenfest matrix of order 4. And the first question that you should be asking yourself, is this a regular matrix? It's not trivially regular, and it's a 4 by 4, so we have to be a little bit more systematic about this. So if we look at our constant m, which in this case is going to be 4 by 1, our Perkins number, 4 by 1 squared plus 1, that's going to be 3 squared, which is 9 plus 1 is going to be equal to 10, so we can just jump straight up to 10 if we desire. So if we look at, for example, p, and let's actually create a little bit shorthand notation. So let's assume that x represents any non-zero entry. Any non-zero entry. So you'll see why I want to introduce this notation in just a moment. So if we look at this matrix P from the perspective of non-zero entries, what you have is 0, x, 0, 0, x, 0, x, 0, and 0, x, 0, x, and then 0, 0, x, 0. So you almost have a checkerboard pattern with a couple little entries missing in both of those corners. But once you actually go up to, for example, p squared, what you're actually going to get is x, 0, x, 0, 0, x, 0, x, x, 0, x, 0, and 0, x, 0, x. And if you go up to, for example, p cubed, so p cubed will actually be equal to 0x, 0x, x, 0x, 0, 0x, 0x, and x, 0x, 0, and it will alternate between these two patterns. So this is going to be the same structure for P4, this is going to be the same structure for P5, and so on for evens and odds. Right? So what exactly is going on here? So let's see if we can get any sense out of this from the diagram perspective. So we have, for example, S0, S1, S2, and S3. So how do I want to represent this diagram to make it look nice? So let's do S0, S1 here, let's do S2 here, and let's do S3 here. Right? So if we have 0 particles, we can obviously jump to 1, and if we have 1, we can obviously jump to 0. This would be probability 1, and this would be probability 1/3. If we have 3 particles, then we're guaranteed to drop on that next iteration, and 1/3 in the opposite direction. And over here, we're going to have 2/3 from 1 to 2, and 2/3 from 2 to 3, and the rest of these arrows are 0. That is, this is going to be equal to 0, 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 and most importantly, this is bidirectionally going to be equal to 0 as well. Right? So it's impossible for a state to communicate with itself. So if we exponentiate this enough times, you should be able to see that we're always going to have zeros in those cross-sectional regions. That is, if we have, for example, p to the power of n, and then we look at the ith element for that, then we're always going to be equal to 0 provided that n is odd. And then you could develop a similar thing for the off-diagonal entries. For example, actually we could do a nicer way. What we can actually do is ij is equal to 0 if, let's see how I want to do this. Let's assume that n is even. So what we can do is I plus j is odd, and it's going to be equal to some non-zero entry if it's even. And if n is odd, what you're actually going to have that pn ij will be equal to 0 if I plus j is even. Because pretty much that structure follows like a reduced echelon form or expansion by minors and cofactor structure. Right? So once you're able to justify these things via dual mathematical induction or whatever principles that you may have behind you, then you should be able to see that Ehrenfest processes are not regular Markovian processes. Right? So that's kind of sad for the Ehrenfest process. Even though they do have several applications, they do not have this unique limiting distribution property associated to them. So what exactly does the limiting distribution of Ehrenfest properties actually have? So let's take a look at the eigenvalues and see if they can shed any light into our problem. So if we find our eigenvalues for this particular matrix, you're going to have 1, you're going to have -1, you're going to have 1/3, and you're also going to have -1/3. And there's only two eigenvalues for this irregular matrix that we need to focus on, and that's 1 and -1. These are usually what we refer to as our unit eigenvalues. Now, there's a lot of theory behind irregular matrices, and we'll get to them in a later time, but I just want to sort of give you a little introduction to them now. Right, so we're looking at our two unit eigenvectors, one guaranteed to be one of them, and what we're going to look at is the eigenvectors for both of them. So V1, for example, is going to be equal to C1 times 1, 3, 3, 1, and if we look at V2, what we're going to actually have is -1, 3, -3, 1. So we clearly see that this vector cannot be made into a probability vector, but we can make this into a probability vector very easily by doing 3 plus 3 plus 1 plus 1, which is going to be 8. So we have 1/8, 3/8, 3/8, and 1/8. So one could ask, is this a limiting distribution for our system? So the easiest way to look at it is to exponentiate our matrix infinitely many number of times and see if there is any pattern. Keep in mind our matrix P is going to oscillate back and forth between even and odds in terms of its structure. So it's guaranteed that this column is not always in one of them. Actually, this cannot belong to Pn for all in the set of naturals because it's guaranteed that non-consecutive entries have to be equal to 0 in that process. Right? So it's impossible for this to be in our matrix. So what exactly will be in those matrices? So let's actually take a look at that together. So if we look at P infinity even, so the even and then take the limit as n goes to infinity, what you're actually going to see is 0.05, 0, 0.95, 0. In the next column you'll have 0, 0.32, 0, and 0.68. Then you're going to have 0.05, 0, 0.95, and 0, and then 0, 0.32, 0, 0.68. So we have a couple very interesting things to look at here. Notice that this column here and this column here are the same exact thing, and this column here and this column here are also equal to the same exact thing. And that's kind of interesting. Who are these little columns in this matrix, right? So let's actually look at the odd case and see if we see anything useful there. So the first column for this is going to be 0, 0.32, 0, 0.68. The next column, you want to take a guess, 0.05, 0, 0.95, 0. Take a guess of the rest of this matrix, 0.32, 0.68, 0.05, and 0.95, right? So as you can clearly see, these two vectors are indeed the same. And if we look at these other vectors here and here, those vectors are the same, and they obviously do match to their even versus odd counterpart. Okay, so that's actually pretty interesting. So what about the limiting distributions dependent on your initial conditions, right? If you start off in state 1, where are you, guaranteed to exist or something like that. So let's take a look at that. So let's suppose that P0 is equal to 1, 0, 0, 0. So we start in state 1, which means we have 0 particles on the left side for the Ehrenfest process, right? So what you're actually going to see for this particular relation is that P infinity even of P0 is actually going to be approximately equal to 0.05, 0, 0.95, and 0. And P infinity odd of P0, we'll take a guess what this vector is. This is actually pretty interesting. 0, 0.32, 0, and 0.68, right? So you get those vectors that are in column 1 and column 2 of the P infinity even matrix, or column 1 of the P infinity and column 1 of the p infinity for the even and odd, respectively, right? And what's even interesting is that you'll actually get the same exact answer if your initial condition is 0, 0, 1, 0, right? So it's the first state and the third state. So I want you to think about this because this is, very beautiful to me. So let's assume that you have p0, which is equal to 0, 1, 0, 0. And also, take a guess. What's going to match for this behavior? 0, 0, 0, 1. Do you want to take a guess at what p infinity even of p0 will be equal to? And what p infinity odd of p0 will be equal to? Take a guess. So this first thing is going to be equal to 0, 0.32, 0, 0.68, and 0.05, 0, 0.95, and 0. Right? So that's actually very, very interesting, right? So we actually have four, well, technically two, well, I guess you could call it four different distributions depending on which iteration of your period you have, because we definitely do have a periodic stationary probability transition matrix. And also the ending state also depends on which initial state that you go in, right? But keep in mind, if you go from here, if you iterate by one more, you will go here. And if you iterate by one more, you will go here, right? So it's always going to cycle back and forth. So that's just an introduction into or just a nice sound foundation of regular Markov processes with a little introduction as to what to expect for irregular Markov processes. Hope you enjoyed this video, and I'll see you in the next one. Take care.